All right, so thank you all for coming. Thanks for being here. It's super nice to see all these faces in person instead of virtually over Zoom. Like Mark mentioned, this is a portion of the work that I did or am currently doing for my PhD at School of Mines. And all of that is done as part of the Mud Rock and Tight Oil Consortium run by Steve Sonnenberg, so MudTalk. Their consortium meeting is coming up shortly, so they'll have all kinds of other neat talks that you can listen to if you are so interested. So without further ado, I'll get started. This is co-authored with Jeff May, and it's Old Dog, New Tricks, a multi-scale reevaluation of the sequence stratigraphic framework in the emerging Mowry Shale unconventional play. I'm trying to win the award for longest title. So some of the things I'll be talking about today, we'll start off with just a brief introduction. I'll introduce you to the Mowry as both a source and a reservoir. We'll talk about what makes up the Mowry, what are its components, and then how do I break this rock apart into different rock types, and just trying to find ways to make this digestible so we can start to think about how we could tackle this as a target for fracking. So to do that, I'll also introduce you to some sequence stratigraphic frameworks that Jeff and I have developed. And so as part of that, we'll talk about flooding surfaces. I know those are your favorite surfaces. Talk about the parasequences that those frame, and then the systems tract and sequences building up from these small parasequences upwards to understand the Mowry in terms of subdivisions that make sense for mapping. So once we talk through that, we'll go through the mapping, basic structure thickness, and then we'll get into what's very important in the powder, understanding temperature and maturity and how that factors into Mowry development. And then lastly, we'll wrap up, starting big with all that mapping. We'll hone down to core scale stuff and talk about core properties of these rocks and some core scale work that I've done as well. And all cycling back to how does that thermal maturity and how does the sequence stratigraphic framework all inform decisions about how do you tackle Mowry as a target? Where would you want to be in the basin? What would your lateral target selection look like? And then how would you go about completing this rock to make the most effective well that you can? So I call this Old Dog, New Tricks because the Mowry Shale has been a petroleum system that we've known about for a very long time, over 120 years. I found this photo taken in 1899 of Plunkett Anticline, where there's a Mowry Shale oil seep. So geologists have known about this rock for a while. We've known that there's oil in it, but it's really taken almost this full 120 years for us to sort of crack the code on how to effectively commercially exploit this rock and get hydrocarbons out of it in commercial quantities. The Mowry Shale is a pretty major source rock in the Powder River Basin. If you work the Powder, you know the Mowry, whether you've looked at it specifically as its reservoir or you've just looked at it for its source properties. It's estimated that it's exposed to over 500 million barrels into the muddy sandstone. And cumulatively, the reservoirs that are sourced by the Mowry have produced about 1.2 billion barrels of oil and 2.2 TCF of gas. Within the Mowry itself, these are some older numbers are from 2009, but it's estimated at about 198 million barrels of oil and another 198 BCF of gas as well. So we know we've got this great source rock, but the Mowry itself only accounts for about 2% of the horizontal wells that have been drilled in the basin. Most of the wells drilled that are horizontal are Turners, the Parkmans, the Niobraras. The Mowry, just there aren't that many examples of it. We're starting to see more of them drilled recently, but there's still only around 50 wells for us to look at to try to understand this reservoir. So we still have a lot to learn. And you can see from the normalized production plot on the right, the wells are getting better as we do learn more, but we can do better still. So some brief background on the Mowry Shale. It sits just on top of the Shell Creek Shale and beneath the Frontier Sandstone. And it's a light gray silicious shale with many radiolarian tests, lots of fish scales, other fish parts, and also marine organic matter, bentonites, ash beds, and varying amounts of detrital silt as well. And we'll see some pictures of those on the coming slides. The Mowry was deposited during a major transgression of the Cretaceous interior seaway along a low angle ramp. And at the time of deposition, unlike something like the Niobrara, where the seaway was connected fully from the north to the south, during Mowry deposition, it was restricted. And so you have a very different sort of chemical setup. That's why you have rocks so different in something like the Mowry that's very silicious versus something like the Niobrara that's got more carbon. In terms of gross thickness in the powder, the Mowry ranges anywhere from about 130 to 250 feet. It's on average about 2.5 weight percent TOC. Porosity is around 7%. So that's not too bad, but it's the permeability that gives people a little bit of heart attack when they see numbers like 200 to 300 nanodarcies. It's a tight rock, but as you'll see, that's not necessarily an accurate average, because as you move around in the basin and you get to certain areas with higher thermal maturity, that number gets much, much better. In terms of water saturation, the Mowry is typically more than, it's about 50%, but the upper portion of the Mowry tends to be even wetter and can exceed 90% in some places. And kerogen, it's mixed type 2, type 3, predominantly a type 2 in the powder, but as you move into places like the Bighorn, you get more of that type 3 influence with more plant material. So those components I mentioned. One of the things that makes the Mowry, makes it so silicious, is this abundance of radial area. So there are these little creatures in the seaway, little zooplankton, and they have silicious shells. And that's why the Mowry has such a biosilicious character compared to some of the other shale units in the basin. So you can see in hand sample these little white flecks. Let me turn on the laser pointer. So all these little white flecks here in hand sample. In thin section, you can see them here in these oval to kind of oblong shapes right here, highlighted by these yellow arrows. And even in cathodoluminescence, you can see these remnants of radiolarian tests. And the dull color that you see here is how you know it's biogenic. One of the other things that makes the Mowry is its abundance of fish scales. It's one of the easiest ways to know that you're in the Mowry when you're looking at it in outcrop. So on bedding plains, you'll see lots of fish scales, you'll see bones, you'll even see teeth. Sometimes you come across rocks like this where you can see actual fish skeletons that are all smushed, but that's very, very typical of the Mowry. Along with that is marine organic matter that typically occurs in these like kind of bedding parallel wisps, and often occurs in conjunction with clays or in what are called organomineralic aggregates, these OMAs. So you'll find the organic matter occurring in association with these clays. The other thing about the Mowry that makes it very unique compared to some of the other units in the powder is the abundance of bentonites. There are many bentonites throughout the Mowry. It's capped by a very large bentonite called the clay spur. The base of the Mowry is defined by another somewhat large bentonite called the Arrow Creek. But throughout the unit, you have tens of these little thin bentonites. Some of them are thicker on the scale of a few inches. The clay spur itself is over a couple feet thick. So lots of bentonites to contend with. Something, I think that gives people a little bit of pause from an operational standpoint because it can cause all kinds of drilling issues, but not something that's really avoidable because they're everywhere. And so you can see here they occur sometimes in these thin beds. The easiest way to tell them in core apart from silts is if you look at them under UV light, the bentonites will fluoresce this bright yellow. And you can tell that they're also reworked because this is an outcrop sample where you can actually see ripple cross-lamination of the bentonite. So these things are getting deposited, they're getting moved around and reworked along with all the other shales that are being deposited. And then lastly, it's composed of this detrital silt component. So while there's, yes, lots of quartz in the Mowry, you have to be able to tell apart the biogenic quartz from the detrital quartz because it contains both. You can see in the cathodoluminescence image here, the detrital stuff really, it's very bright, so you can tell it apart from this more orthogenic quartz that's occurring in the background as this microcrystalline quartz. So I break the Mowry apart into 6 main facies. The first one is a bentonite, and the rest of them are these shalier facies. And what you'll see, I've arranged them in order of decreasing silt size or decreasing silt content. So you start off with the bentonite, and then near the top of the Mowry is this bioturbated sandy mudstone. It doesn't always look quite like this where it really stands out quite so much, but it's got lots of bioturbation. You can see all these little furrows throughout and a fairly large sized quartz grain. Next, I define a thickly laminated silty mudstone. This is also most common in the upper portion of the Mowry. The silt is a little bit smaller in size compared to the previous facies. And you can see these laminations vary in size from, very, very thin, but there's also these internally cross-laminated beds across as well. Then I define a thinly laminated silty mudstone. This is most prevalent in the lower portion of the Mowry. And you can see here, the silt grains themselves are a lot smaller than the facies I just showed you before. And you can see the scale of these thin laminations. This scale bar right here is 400 microns. So it's very thin bedding compared to what you just saw. And then these last two facies are most prevalent in the middle of the Mowry. And these are the facies that contain the highest proportions of biosiliceous material. So these have the most biogenic silica in them, the least amount of detrital silica. And you'll note that absence of those detrital silt grains throughout here. There are some, but they're not nearly as large and not nearly as abundant as in the previous facies. So without knowing it, taking a sequence stratigraphic approach in shales kind of started off from Nixon in 1973. I don't think it was really intentional, but he published this paper and divided the Mowry into two main units. He called it a lower and an upper. And he noted that it was thicker toward the northwest, it thinned toward the southeast. And the way that he defined this upper and lower was by mapping what he called marker beds. So unintentionally, I think what he ended up doing was mapping out these flooding surfaces for us, which formed the basis of coming up with a sequence stratigraphic framework for the Mowry Shale. So I've highlighted some of these flooding surfaces for you here with these blue dashed lines. And these flooding surfaces represent time periods where there's an abrupt shift of facies that would either tell you the relative sea level has increased, you're in deeper water, or there's been some sort of a decrease in the sediment supply that's sourcing out into the basin. And so these flooding surfaces themselves sort of demarcate these packages that form parasequences. And you can see those parasequences in outcrop as these benches. As you walk across Mowry outcrops, they're almost like little kind of hills that you're traversing over. And each of those represents a Mowry parasequence. And typically what you see is that those are more argillaceous or clay-rich at the base, and then they become more siliceous up at the top. And so these are just some examples of those. Sometimes they have bentonites that define them, not always, but that's pretty typical of what you see. I do want to note that you don't always see that trend of going from argillaceous at the base to siliceous at the top. As you get more distal in the basin, that trend actually switches, and you're more siliceous at the base and you become more clay-rich at the top. And the reason for that is that as you go more distal in the basin, the base of your parasequence is going to be composed predominantly of more of this biogenic material. And then as you move up into that parasequence, you're getting more of the clays. So that's going to make the gamma ray look a little bit hotter. So you get a reversal of that signature. So it almost looks like, it's like, instead of cleaning up like you see here, you get the reverse of that. And you can see that in cross-section, going from more proximally in the Green River Basin out more distally towards the Wind River, towards the Powder. In this uppermost parasequence of the Mowry, you go from a coarsening up or cleaning up cycle in this gamma toward switched here where you're cleaner at the base and then getting more clay-rich up at the top. So previous attempts at applying sequence stratigraphy to the Mowry look something like this. There's one example from 1998, another example from 2007. And generally, these would explain the Mowry as a transgressive system tract or increasing sea level through the Shale Creek that continues into the middle of the Mowry. You reach maximum seaway inundation somewhere in the middle of the Mowry, the max flood surface, and then you start to get propagation of shoreline deposits, and you get into this high stand systems tract in the upper part of the Mowry and into the lowermost part of the frontier. And you see a somewhat similar interpretation here in 2007 as well. They defined a couple sequence boundaries, didn't really put a flooding surface in there. But these models don't necessarily give us a meaningful way to subdivide the Mowry internally. They just sort of say they're flooded and then it starts receding. And so what we're attempting to do here is sort of apply more of a high resolution approach to subdivide the Mowry itself into some internal packages that we can then evaluate in terms of their rock properties to understand maybe how you'd want to more intentionally target these zones. So to do that, first we have to take a little bit of a step back and think about where are we in the basin? What's the most appropriate way to apply this? So the Mowry was deposited along a low gradient ramp, very, very shallow, less than 0.01 degrees. So in a system like this, you're not going to see any low stand fans. So you're not going to expect to see any kind of low stand systems tracks, nothing like what you get in, let's say, the muddy. In the Mowry, you would expect that the transgressive systems tract is going to be very thin as you move basin where it might not even exist. Essentially, that max flood surface is going to sit right on top of your sequence boundary. And the sequence boundary itself is maybe a little different than what you're used to thinking about. You're not going to get these really stark contrasts in lithology like you might get more proximally, where you're going from silts or muds and then being capped by shales. It's not going to look that way. It's going to be a little bit different where you don't think of it as an erosional boundary. When you're farther out in the basin, that sequence boundary becomes a correlative conformity. So when you're looking for these things in core, it's not going to slap you in the face. It's not going to be really obvious. It's going to be very, very subtle. And so you have to look for subtle shifts in the amounts of silts and clays that you're seeing. So how would you go about applying that to core? So here's an example of the educated guess. This is located in the northern Powder River Basin. And we'll step through and we'll put some of these important surfaces on there. So we start off with one flooding surface down here. And wireline log, it looks like this. That's the surface right here. You see the hot gamma kick, and that's that bentonite that's hiding underneath where it says flooding surface right there. We can move to the next one. Another flooding surface here underneath this big bentonite. That's gonna be this bentonite right here on log. Another flooding surface here. That's that flooding surface. And then you'll notice these two bentonites right here, these two big ones, we can put flooding surfaces there as well. So if we mark those on the core, we can see what they look like in wireline. Great. If you notice, it's very subtle, and it might be hard to see with this projector here, but as you move from farther or from deeper down in the core and as you shallow up, there's a subtle increase in the amount of silt. You can also notice it as this is a little bit darker gray and you're starting to get lighter gray as you move up to the top. So this coarsening upward cycle here, we're going to go ahead and put a sequence boundary right there and say that's the top of the sequence, which makes this the condensed section. And so all of these core boxes in essence reflect one high stand systems tract, or one instance of pro-grading shorelines farther toward the shore that we're not necessarily seeing out in the basin as something very stark. We're seeing it as a subtle increase in silt content over here. And so if we put that as a sequence boundary, then this interval in here becomes your transgressive systems tract, which we said was going to be very thin to almost non-existent where we are, so that's the case. And then it's going to be capped by this condensed section right here. So we can go ahead and put those surfaces out on the logs. And by doing this through and iterating with a number of different cores, you can start to build a basin-wide model and map out these important surfaces. So if we look at a correlation going from the Bighorn Basin out here and then moving down to the southeast, we can essentially just do the same thing. We'll put those flooding surfaces on there. So you have all these different flooding surfaces that you can correlate across. And then we can decide which ones we feel are those sequence boundaries based on what we're seeing in the core. And then those sequence boundaries themselves are going to capped by condensed section at the place for bentonite. Those sequence boundaries are then going to define what I'm calling the lower, middle, and upper Mowry. So these aren't just arbitrary subdivisions, they're actual cycles of high stand systems tracts or cycles of progradation that you're feeling this subtle way further out in the basin. And so I want to draw your attention to this one package, for example. You see where the sequence boundary is, and actually let me back up so you can see it clearer. We have one log on here that has a lith log, and it's a little bit faint on your screen, but there's a sand right here that sits just underneath the sequence boundary. Similarly, there are two sand packages that sit underneath this sequence boundary here. And then also at the top of the Mowry, there's another sand sitting underneath this sequence boundary. So when you're further out in the Bighorn Basin, these are actual sand bodies. So if we focus on this package, for example, this is what's called the Kimball sandstone. There's the Kimball, and just beneath it, there's another sand called the Ochlui. But this is an honest to goodness sandstone in the middle of something we call the Mowry Shale. It's a sand that as you transition more distally out into the basin, once you get over toward the Powder, it doesn't look like a sand anymore. It looks like a shale. It looks like a silty shale, but it's a shale. And so this framework is really helping us understand what do things look like as you're more distal, and then how does that translate to what those packages would look like more proximally? How might you want to think about targeting in here if you're trying to look for things like increased porosity and permeability? You want to find things that are correlated back to some of these sand bodies potentially. So using this framework and using these surfaces, we can start to map out the Mowry in the basin. We'll just start off with some general mapping here. This is what the structure looks like The powder is steeply dipping on this western side here and then more shallowly dipping on the east. And then I've outlined for you the 8,000-foot contour, and that's generally what we think of as being the active pod of generation for hydrocarbons. And then Mowry thickness, as I mentioned, thins as you move to the southeast. So the sediment source is up here, perhaps a little bit of sediment input down here as well. You've got a little bit of a thick. You can see that better when you look at the gross thickness maps, specifically of those upper, middle, and lower units defined by the stratigraphic model that we just talked about. So for the lower Mowry, it's thin, but it's thicker up toward the northwest and then thins to the southeast. Similarly, the middle Mowry has a very, similar trend, but also that slight thick package that I mentioned before. So perhaps some sort of sediment input over here. And then the upper Mowry also thick toward the northwest, closer to the source of the sediment, and thinning as you move down to the southeast. But more importantly, if you've worked with powder, you understand the importance of temperature. This isn't just about how deeply things are buried, but it's about where they sit in the basin. And so temperature and maturity in the powder is very, very important. So these are two different ways of doing thermal maturity or temperature mapping in the basin. This one on the left here is based on cuttings, and that's Tmax data. It's got a contour interval of about 1 degree Celsius. And so you can see these hot spots that come up right here toward Congress and Campbell, and then further south in Congress County. And these are 3 known mapped hotspots that come out in the cuttings data. You could also look at it from DSTs, so a completely independent data source can come up with the same exact hotspots. So what I've done here is map the top of the Mowry temperature by looking at DSTs taken from the Muddy all the way up to, but not including the Niobrara, coming up with a geothermal gradient, and then applying that back toward the depth of where the Mowry, where the top of the Mowry comes in. And so this is a contour interval about 10 degrees Fahrenheit, and totally independent data sets, but they give you the same exact hotspots, these 3 hotspots right here. And we'll see when we look at the core data how those really are going to influence the reservoir quality of this rock. Likewise, if you're looking at it from a petrophysical perspective, whereas in many basins, resistivity is going to correlate strongly with depth. This is something that's been known, it's been published since 2012 from this Monaco-Lapierre paper on the Mowry, but depth and resistivity do not go hand in hand here. It's really a story of resistivity and thermal maturity. The correlation between those two is much, much stronger. So before we can get into the core data, I just want to briefly run through what core data is available, what we have at our hands to kind of tackle this problem. So there are 7 cores available. They're mapped out on here for you. 6 of these have near complete Mowry. This Java state only has mostly the middle Mowry, so it doesn't have lower and upper. And this data set includes 200 data points of mineralogy, crushed rock data for things like porosity and permeability and saturations, and then also rock eval data points as well. And the samples that we have represent all the major facies that I described, and it spans the entire Mowry, so it's got lower, middle, and upper, fairly equally represented, and also spans this range of maturity, which I'm showing you down here. So we're going all the way from immature in the oil mountain core up to into the condensate window with what I'm calling Mowry 4. So these cores here are proprietary, so you'll see them just labeled as Mowry 1, 2, 3, and 4. And I'll stick with this color scheme for the rest of the slides, where the cooler colors are going to represent lower maturity samples, and then the warmer colors, particularly these pink and reds, are going to represent the more mature samples. So in terms of character quality and type, we already talked about this. It's predominantly a mix of type 2 and 3. These samples down here are plotting in this gas-prone area, but that's really just because they're higher maturity samples. So by and large, throughout this basin, you're dealing with an oil-prone source rock with a very minor contribution of some land-derived material as well. So if we want to look at some of the rock properties, we can do that first in terms of the facies that I defined. And if you remember, those coarser facies, the bioturbated sandy mudstones and the thickly laminated silty mudstones are most prevalent in the upper Mowry. The thinly laminated silty mudstone is most common in that lower Mowry subdivision, and then these silicious mudstones are more common in the middle Mowry. And here you're looking at median TOC, water saturation, porosity, and permeability values. And so what you see is these coarser or siltier facies, so those that are colored in yellow and gray, tend to have lower average TOCs. They tend to have higher water saturations. The porosity is moderately increased, but not terribly significantly. but you do see higher permeability, especially in this bioturbated sandy mudstone. So the trends here aren't particularly stark, but if you look at it in terms of permeability versus porosity and you size this by oil saturation, you start to see that the most oil saturated samples are represented by those biosiliceous spaces. So the biggest bubbles you'll see here are in these blues and these reds, and they tend to sit at the lower porosities and lower permeabilities. So you'd think those higher oil saturations are probably held up in some of the smaller pore sizes. But more informatively, you can start to look at these samples divided a different way and look at them in terms of their thermal maturity. So here I'm representing them by core. And you have the least mature core here in the blue, and then increasing thermal maturity as you move to the right. And here you have bulk mixed illite smectite, you've got water saturation, you've got porosity, and then you've also got permeability. And these trends, I think, are much more interesting than looking at it by rock type. So what you'll notice is that the more mature cores, they have lower mixed illite smectite. That's not a surprise, that's been documented in plenty of papers. But the water saturation dramatically decreases. So you're starting from something around 80 or 85 and going down to around 65. So dramatically better oil saturations as you increase your thermal maturity. Porosity is a little bit more of a sort of confusing trend. You decrease, you come up a little, and then your porosity actually decreases somewhat as you get into these more mature samples. That could be because of some, blocking some of the pores through maturation. But permeability, I would argue this is the most important trend that comes out of this data set. So starting with that Java state core and then moving up through that thermal maturity transect, you're essentially increasing your permeability almost 25 times by moving from this educated guess core that sits at around basically the early onset of the oil window. You're increasing your permeability 25-fold by the time you get into the condensate window. And that really correlates very, very well with thermal maturity. And then you can start to break this apart and become even more granular and look at it in terms of those sequence stratigraphic subdivisions that we talked about before. So here I'm showing you colored by each core, upper, middle, and lower average values for, in this case, TOC. And so consistently you see that the middle Mowry has the highest TOC, followed by the lower Mowry, and then the upper Mowry has the lowest amounts of TOC. And that trend continues for every core. So regardless of where you go in the basin, that middle Mowry always has the highest TOCs. Similarly, in terms of water saturation, you see that the middle Mowry has the lowest water saturations, and that's consistent across these cores. And that's superimposed on the overall trend of lower maturity here, getting improved and improved hydrocarbon saturations, lower water saturations as you move to this Mowry 4 core here. And then in terms of permeability, this one's a little bit trickier to look at, but you see low permeabilities in the middle Mowry. These are the kind of numbers that would give people a little bit of pause and go, oh, those don't look very good. But once you cross this threshold and you get towards this core Mowry 3 and you get to Mowry 4, you've crossed some sort of threshold, and now all of a sudden your middle Mowry permeabilities dramatically increase. So just by crossing this thermal maturity threshold, you go from having very low permeabilities to permeabilities that actually exceed what you see in the lower and upper Mowry. And that's true of both Mowry 3 and Mowry 4. So we can look at that same permeability and porosity cross plot here. And now I'm coloring them by thermal maturity. And if we superimpose a trend on there, what you're seeing is these shallowly buried immature cores going through compaction and the loss of permeability. We come around to educated guess here early in the oil window, and then we start to see permeability and porosity slowly increase with thermal maturation. So you're creating pores, you're creating pathways as you mature these hydrocarbons. So you could think of this in a different way and just map thermal maturity versus permeability. And you get this cross plot. And what I did here was combine a few data points, that's these X's, that were taken in things I found in the literature. So taken out of Zach Collins' thesis on the Mowry and Ethan Melville's thesis on the Mowry, and confirmed this isn't a trend that's an artifact of my data set. This is truly what the permeability and thermal maturity data looks like when you cross plot them. So you see this trend of increasing up to around a Tmax of about 450 degrees, and then it levels off. And one potential explanation for this trend comes back to that Monica and LaPierre paper from 2012. So one of the things they did was model carriage and what they called carriage and porosity for a range of initial TOCs. I think a lot of us would probably be happier calling that organic porosity, but that's a discussion for another day. And so what you can see on their plot is the greatest rate of change in organic matter porosity is developing in this range from an RO of about 0.7 to 1.0. Thought of in another way, you could look at a plot of transformation ratio versus thermal maturity. And again, you see that over that same maturity range, that's where you get the greatest change in transformation ratio, which corresponds exactly with where we're seeing an increase in permeability develop and then eventually flatten out. So what we're seeing here is some sort of effect on the organic material from maturing these samples over these hotspots. And that same sort of trend holds even if you look at it in a different way. So I've done quite a bit of nitrogen absorption work as well, and you see a similar trend. So this plot here is what you just looked at, but I've only taken the biosiliceous species. So it's that most biosiliceous species that's common in the middle Mowry. And again, same trend you see at lower Tmax, and then as you increase your thermal maturity, your permeability increase and then start to level off. Down here is that nitrogen absorption data, and I'm plotting that for educated guess, and then Mowry 1, 2, 3, and 4. And what you see is that the total pore volumes you get from nitrogen absorption, they're highest in the educated guess. It hasn't gone through really much transformation yet. As you start to increase the thermal maturity and get closer to about a 1.0 in these Mowry 1 and Mowry 2 cores, you lose some of that pore volume. Perhaps from early organic matter transformation, I don't know, it's still kind of a question mark in my mind. But then as you continue maturing these samples and you get up to a 1.2 and then increase it even further to a 1.3 in these cores, Mowry 3 and 4, that total pore volume dramatically increases. So this increased thermal maturity is affecting measurements of pore volumes, it's affecting measurements of permeability, it's real, and like I mentioned, these hotspots are really going to contribute to where we're seeing those increased pore volumes and those increased permeabilities. So what do you do with all this information, trying to aggregate all of this? We've got this reservoir quality data, we've got pore data. How do you use that to actually make meaningful decisions? So you can start to think about all those things in terms of how would you go about targeting a well? And right now, most operators are targeting this middle Mowry zone. Some are targeting down in the true middle of the middle Mowry, others are targeting a little bit higher up. But we understand that this is probably one of the better places to put your well because it's biosiliceous, it's going to have the highest organic matter content, it's going to be brittle, it's going to be favorable for fracking, it's TOC rich, it's got all the things that you want, you're avoiding the high water saturations up here, and it looks like it's better rock quality than what you're seeing down in the lower Mowry as well. So zooming out a little bit and then taking these concepts of thermal maturity, how does that actually play out in terms of well productivity in the basin? So this is that same top of Mowry temperature map that I showed you before that was generated from DSTs. And we can move those same hotspots over and look at a map of 6-month BOE that's been normalized per lateral foot. And the best performing wells, surprise, surprise, all occur on top of these hotspots. This is slightly out of date. There are a few more wells that have been drilled down here that are quite good, as well as a couple of wells up here as well. So this trend continues to hold as more wells are being drilled. Interestingly, since we don't really have a lot of Mowry data points to put on this map, something else you can think of would be to look at muddy sandstone results. So you can look at the oil gravities that were measured in muddy sandstone wells, since that's sourced by the Mowry. And if you plot those same exact hotspots and you look where the muddy oil gravities are highest, you see them occurring up dip of these hotspots where you'd expect increased generation and higher permeabilities, easier to move fluids out of the Mowry into the southern zone. So all of this is telling the same story. The hotspots are really key to thinking about where you want to be in the basin. So we know where you'd want to drill in the Mowry stratigraphically. We understand the middle looks to be the best. We understand that you want to be on top of these hotspots, but it's not just where in the Mowry you drill and where in the basin you drill, but there's also this component of how you complete the well. So looking here at the trends in proppant per foot versus 6-month BOE per foot, so all this is normalized, we see that you get better wells when you use more proppant, and similarly, you're getting better wells as you use more fluid. At some point, yes, there's going to be diminishing returns on that, but the general trend is to have higher amounts of proppant, more fluid to move that proppant, and that is resulting in better wells. Another trend we're seeing in Mowry development over the last few years is an increase in lateral length, which to me is really telling you something about the confidence that operators have in this target zone. You're not going to drill 2-mile wells if you're not super comfortable with the zone and feel like you've got a good handle on it. So it's nice to see that these things are, not only are we drilling more of these wells, but we're drilling them longer, and it's resulting in better wells as well. Looking at completion metrics over time, this is starting in some of the earliest horizontals in 2006, and again, slightly out of date from 2019, so pre-pandemic, but the same trend here of more fluid per perfect foot. Operators are using more proppant per perfect foot. They're going for more stages that are shorter to try to stimulate the rock better and get better fracs and move more of the fluid out. So higher fluid concentrations, more proppant, more stages, shorter stages. And then what's really exciting lately is that we have the first few tests in the ground where we're not just drilling parent wells, we're not drilling one-offs, we're actually putting the Mowry into development mode. That's pretty exciting. So starting in 2001, we had the first few examples of this. And these are definitely wells to keep your eye on if you're following the Mowry and wanting to see how it performs. If you do follow it, you know which company drilled these. And on the bottom there, you can see a timeline from spud to completion. There have been 4 different leases drilled with 3 and 4 well pads. And whether it was on purpose or not, the MWD data was published on the WOGCC website. So you can still find these for a number of these wells. And so you can actually go and backsear them and see what this operator is targeting. And sure enough, this is the upper Mowry here, this is the middle, this is the lower. And this well is drilled consistently throughout the middle zone of the Mowry. So that seems to still be what operators are doing. That seems to be what's working. These wells will be really interesting to keep an eye on because they also have a number of different spacing tests. So the first package that was drilled at around 1,000-foot spacing. And this particular operator felt that 660 was something that they could push forward. So they tested that as well. If you look at the production results, these are maybe not quite as encouraging. I think the answer is going to be something closer to this 1,000-foot spacing. 660 might really be a little bit tight, but now we actually have some wells in the ground that we can go look at and see, you know, how is this reservoir actually performing? What happens when you go into development mode? Don't just drill parents, but you're actually offsetting it and you're dealing with depletion. So these will be really, really interesting to follow. Just an exciting thing to keep an eye on. So with that, hopefully you all have been able to finish your lunch and I can conclude. I'll just wrap up by summarizing some of the things we talked about. So we talked about the Mowry being composed predominantly of this biosilicious mudstone that's recrystallized radial area, varying amounts of detrital silt in there, but overall it's that biosilicious mudstone that's going to have the highest hydrocarbon saturations, lowest water saturations, and overall the most favorable properties in terms of lateral target. We talked a little bit about the sequence stratigraphy of the Mowry and this new sort of high frequency approach where we've subdivided the Mowry into a lower, middle, and upper zone consisting of multiple thin pair sequences where we see an upward increase in silt and bioturbation. And those can be arranged into these 3 regressive high stand systems track. That's that lower, middle, and upper. And perhaps, we didn't really mention this too much, but maybe there's a low stand sitting up there at the top, so you didn't mention that. We talked a little bit about the mapping and the importance of those hotspots in the basin and how they really influence the development of reservoir quality and permeability in the Mowry, and that those increased maturity samples are the ones with the lowest illite cementite ratio, lowest water saturations, highest hydrocarbon saturations, the best porosities, the best permeabilities, and most favorable GORs too to help move fluids in the reservoir. And so it's those coarser grained facies that we find up at the top that have the most extrabasinal silica, higher porosities, yes, higher permeabilities, yes, but that comes along with lower TOCs and high water saturations. So a zone that probably is best to stay away from, where organic and clay content and silica diagenesis are influencing the pore development, and that increased thermal maturity is really helping to create those pore networks within the organic material. And then lastly, I touched on the horizontals that have been drilled and how they're typically targeting the middle Mowry zone. And I would think that the best zone within the middle Mowry to target would be near the top of that middle high skin system stretch, where you're going to sort of get the best combination of detroital silica and frackability, still be able to stay away from water saturations in the upper Mowry, but not necessarily give anything away in terms of the production that you get. So with that, I'd like to just mention a few acknowledgements here. My co-author, Jeff May, who's sitting right over there. I'd also like to acknowledge the Mud Rock and Tight Oil Consortium that's run by Steve Sonnenberg at Colorado School of Mines. And also, I'd just like to thank RMAG, the RMAG Foundation, the Clough family. I was the recipient of the Robert Clough Scholarship, and that was really instrumental in helping me move my degree forward and continue the research that I've been working on. Also, the University of Wyoming, they helped tremendously with the core work that's been done. I only touched on that here, but there's quite a bit of that that will be in my dissertation. Centennial Resource Development was really helpful in terms of helping with funding for tuition and all of that. And then some software and data as well. IHS, Roby, Starsteer has been huge in helping me backsteer these wells. Spotfire for doing all the data analysis, and also Enverus for being able to look at all this completion and drilling data. So with that, I would be happy to take questions if you have any, or you can just finish eating your lunches. Yeah, Justin.
Have you noticed any difference in quartz crystallinity for maturity?
So Justin asked if you've seen any differences in quartz crystallinity as a function of thermal maturity, was that what you were saying? So I don't have a tremendous number of samples. It's a really small data set. So I haven't, the trend that I see in terms of silica crystallinity, you're talking about like a silica crystallinity index. So what you see is pretty much throughout the Mowry, the silica or the crystallinity index is pretty low. And then as you get into that uppermost Mowry where I described that coarsest bioturbated sandy facies, it dramatically increases. It's like you cross this one point and then boom, the crystallinity gets much closer to what you see for a quartz. I can't remember an exact number off the top of my head, but you're going from a 2 further down to something like, I want to say it might be like a 6 or 7. Does that sound about right to you? But I only have about 1 data point per core. So that's 1 data point for thermal maturity. So the variability on that, the differences in XRD, it's hard. I don't see a difference, but it's hard to say that it's not there because just statistically, there could be enough error in that I'm missing it. Yeah.
Yep. I have a couple of questions. First of all, nice talk. How do you know the slope angle so well of the Mowry? The 0.01.
Okay, so he asked, how do we know what the paleo slope of the basin would be? And that's something Jeff and I have talked about quite a bit. And just by making cross sections, and Jeff, do you remember what compaction number when we were doing those kind of, was it like a 10-to-1 for these?
I was using a 4-to-1 decompaction. So I was taking each individual pair sequence, decompacting 4-to-1, running up from Cody all the way down to the Power Basin, and then just figure out the trigonometry on it.
And
it's pretty astoundingly low.
And it's consistent among the pair sequences too. It's not like you do it for one and it's low and one and it's high. You're sort of repeating this exercise and you're getting these very low numbers. So it seems like this was just a very flat place.
That's another one. So you talked about the hotspots in the basin, and they seem to line up with the structure, some of the structural lineaments, the deep-seated structural lineaments that go through the basin. Do you think that some of that could affect the porosity and permeability because there might be increased fracture zones around those big structural zones?
So you're asking if what's leading to the increased permeability in the Mowry is because it's fractured?
If that could contribute.
You know, I suppose it could. I've never seen anything like seismic to know about really like fractures, faults, or start to get at maybe some of those things. You know, could it contribute? It could. I don't really have access to any data that would lead me to be able to say yay or nay. But I can say that the core data that I do have and the permeability increases that you're seeing just on those core samples, so from crushing it up and essentially taking all of that fracturing out of it, is so stark. Even that alone seems to be enough to sort of contribute to why it's working better over these hotspots. But I certainly couldn't say no, that's not contributing to it at all. Yep.
Can you say if the high water saturations in your upper hydrogenated detrital silts improve at the highest maturity levels or not?
Ooh, I'd have to go back and look to see if they get better over there. My guess is no, I'd have to go back and look. I don't know. I don't remember off the top of my head what those look like when I just look at that facies across it. I have to look. Randy, did you have a question?
Yeah, is there bentonite dispersed throughout the Mowry?
Just within, you mean like within the shale itself too?
Yes.
So,
Because if there isn't, why would your flooding surfaces so align with your bentonites?
well, so for one thing, not every flooding surface is a bentonite. There are definitely examples. Oh, sorry, let me back up. Ronnie asked if there were bentonites dispersed throughout the Mowry, so dispersed within the shales. And if yes or if no, why are these flooding surfaces correlating so well to these bentonites? One thing I've always thought of is, well, if you have volcanic activity, you have volcanic activity for a reason. And especially the formation of this basin and, you know, sort of far field effects coming from what would have been like the Paleo coast and plate subducting. If that's happening and that's kicking off an episode of volcanism, it's conceivable to me anyways that that's also going to have an effect on what sea level is doing. You have these little like burps of volcanism, and so they're coinciding with each other, and they don't always coincide, but they can. And that's kind of how I've thought about that. But also even on those flooding surfaces, sometimes there's not even just one bentonite. You can see like an amalgamation of multiple bentonites. So it's like these episodes of repeated volcanism. But that's kind of how I think of it, why they would go hand in hand together. Yep.
Have you tried to correlate maturity with cluster developments using open hole logs all by themselves?
Yes, so I have done some of that. Part of the problem with, the question was if I've correlated thermal maturity with porosity from open hole logging. So one of the issues is, at least for me, I'm by no means a petrophysical expert. So trying to handle the log vintages, because you've got these open hole logs ranging over decades and the quality of those has dramatically improved. So throwing all of the logs that you have into one pot and trying to map off of it, you end up, the porosity mapping I've done looks very patchy. And so I think someone more talented than I am that can maybe resolve some of the vintage issues and maybe help work to do some normalizing on those might come up with something that looks a little bit nicer. But from what I've seen and done, when I try to make porosity maps off of just like a DFE log, it looks very patchy. You don't get the same clear trend.
You really have to have the density and the neutron log.
Yeah.
To be able to do that kind of stuff.
Yeah, and that's just not something that I've spent a ton of time doing. I think it would work where you would probably see some improved porosity there. It's just not something that I've taken the time to work through. Yep.
You mentioned that the bentonites in a lot of cases have indications of minor or significant traction transfer, cross bedding, cross lamination. Not much about the significance of that, why that is that in any way related to the the fact that they're tied to flooding surfaces more than the onset of volcanism itself. It's more of a more climactic related, something that's moving that bentonite from where it is, where it started, where it came from, into the basin through traction transport. I've noticed the same thing in lots of other bentonites, lots of other basins. Right?
So the question was, given all the sort of traction features that you see in some of these bentonites, whether that sort of played, if I'm understanding the question right, if that plays into why you're seeing those flooding surfaces correspond with bentonites. I have to think about that for a second. I don't know if you have an immediate thought on that, Jeff. because I mean, to me, those things you're seeing in those bentonites, they're not necessarily different from the sedimentary features you're seeing in the shales too. It's just that you see them easier in the bentonite, so maybe they stand out a little bit more, but you still get, you know, ripple cross lamination, other traction deposits pretty much throughout the whole Mowry if you look for it. When you look at those silt beds, you see them there too. They might look like planar lamination just because they've been so, you know, smushed and compacted, but you really see evidence of traction sort of features, I'd say, throughout pretty much the whole Mowry, really. So I don't know, I have to think about that one a little bit.